Our next speaker is Gábor from University of Helsinki, and he will talk about the challenging simulation of rotating universes. Yeah.
Thank you. So today I will talk about rotating universes. So let's start with a short introduction. So observable universe, almost everything what we observe, rotating. So planets, stars, solar system has net angular momentum, black holes, galaxies, clusters of galaxies. So the question arises naturally: does the universe rotate? Oh, that was. I'm missing a slide here. Something went wrong. Anyway, so yes, there are some complications with it. So, for example, rotation can break causality because the closed time-back curves would appear if the rotation speed is too high. Also, there are many other issues. So, for example, it's the inflation. During the inflation, the rotation scales with the fifth power of the scale factor. So any inflation would basically destroy rotation in the observable universe. So there are many problems with that, but a small amount of rotation is still possible. And a small amount of rotation could resolve the Hubble tension. So Balázs Szigeti has a very recent article about this. He will give a separate talk on Thursday, I believe. It would explain some observed asymmetries in galaxy spins. So Shamir this year claimed that he found the rotation of a strange asymmetry in the rotation of observed spiral galaxies. So he found like 50% more galaxies that are rotating in the opposite direction as the Milky Way, as in the same direction, which is quite a big number actually. And also that will explain a weak anisotropic expansion observed in few surveys, like in cosmic flows. So to quantify these effects, we have to run simulations of structure formation. So just a very short introduction about the structure formation. So the growth of the structures are governed by isotropic gravity. And there are two main stages of this growth: the linear structure formation, in which the fluctuations are small, and every modes are evolving independently, and the linear growth factor is scale independent. And of course, we have nonlinear structure formation, in which the Fourier modes are coupled. Growth is scale dependent, and dynamics is complex overall. So we need n-body simulations to fit that. And this is the power spectra, different curves representing different redshifts. So the early stage, everything is linear. At late stages, the small scale becomes nonlinear. So, okay. So this is the missing slide. Anyway, so we want to run n-body simulations to follow these structure formation. So the most used topology in simulation is a periodic fritters or periodic box, in which we have a box in which dark matter density field represented by particles, and we solve the equations of motion in this periodic box. And it has many great advantages. So, for example, the linear momentum is conserved in this topology because we have translational equivalence. The fast Fourier transform can be used for long-range force calculation. So we can use that. This is called the particle mesh method. And of course, constant resolution can be used in a whole simulation box without any edge effects. So that's great, but we have a very big disadvantage that the Lagrangian in this topology is not invariant under rotation. So the angular momentum is not conserved in a periodic box due to the Nether's theorem. So why is this? Because if we want to calculate the interaction between these two particles, we have to use not just the nearest neighbor, but all of the neighbors. So we have to do this sum, which is called the Ewald summation. And basically, we are summing up for these natural number triplets. In the ideal case, to be infinity, and this has in practice a cubic symmetry. So if we want to use simulate structure formation with rotation, we need a cosmological simulation method that in which the angular momentum is conserved. Luckily, we have one. It's called StePS, so stereographically projected cosmological simulations, and it works in such a geometry. So in short, we map the infinite spatial extent of the universe into a finite volume using compactification. In the working implementation, we're using inverse stereographic projection. So if we have a plane, we can map this infinite plane into a surface of a three-dimensional sphere. And we do this the same thing in one-dimensional higher. So we have a three-dimensional infinite universe and map everything into a surface of a three-dimensional hypersurface of a four-dimensional sphere. And the initial particle log is a homogeneous sample in this compact space. We generate the initial conditions, and after that, the equations of motions can be solved in a spherical symmetry, compact or non-compact space. And in this case, the Lagrangian is invariant under rotation. And the result is basically a zoom-in simulation with smoothly changing resolution in a spherical volume. So inside we have high resolution region. As we move outwards, resolution will become worse and worse. Yeah, we can follow the evolution of these structures in here. It looks like this. This is an example simulation. Okay, so the equation of motions can be solved in compact and in non-compact coordinates. The existing spherical StePS implementation using Cartesian coordinates, because it's just faster to calculate the distance between 2 points in this coordinate system. And this is how the equations of motion look like. So we have a smooth gravitational force between the particles. And if we are in moving coordinates, we have a Hubble drag term, and we have one extra term to keep the simulation in balance. So basically, this guarantees that in moving coordinates, the simulation will not collapse. This is a radial force. We can also run simulation in physical Cartesian coordinates. In this case, we just only have a gravitational force between the particles. And that's it, because in this case, in the initial conditions, we have to have the Hubble flow, and the simulation automatically trees the expansion. So as my sphere expands, the gravity will slow down the expansion. If you want to add lambda to this picture, we can do this as a radial force again. So the picture is very clear. But we have one other complication before moving into rotating simulations, that the rotating cosmological models are inherently anisotropic. And in a StePS algorithm, we assume spherical symmetry. So if I go back, in this part, we are adding radial parts to the equations of motion to keep the simulation balance or dark energy. So if the simulation is rotating, that spherical symmetry will break, and basically simulation will not work as intended. So the solution, we use compactification only in the x and y coordinates, while having a periodic boundary along the z coordinates. So it looks like something like this. Along the cylinder axis, we have high resolution region, and as we move outwards, the resolution will become lower and lower. And the whole simulation has a cylindrical symmetry. So to keep the simulation in balance in moving coordinates, we have to introduce a radial force that only depends from the perpendicular distance from the axis. And since we are using about summation along the z-axis, this radial force can be calculated as a gravitational force of a finite cylinder. And this was solved in 1988 by Chang. So we are using this formula for the radial force. It is much more complicated what we have in a spherical case. And we added this new boundary condition to our cosmological empirical StePS. So we run our first simulation in this topology. we use standard lambda CDM cosmology with a simulation radius of 500 megaparsecs. The cylinder height was 1.5 gigaparsecs. We have this is just a test run, so we have 1.6 million particles, and the mass resolution at the center was 10 to the 12 masses. And this was run less than a day on desktop PC. And it looks like this. So in the left-hand side, you see the whole simulation volume. In here, we are zooming into the center. And this should be the particles, although the quality of the video is not that great. Anyway, and now we have the simulation, so now we have to analyze those. So we have to calculate the power spectra. So the usual fast Fourier transform-based methods are not working because we have different topology. We have zoom-in simulation, so the small scale modes are only resolved around the central region. And also we have a problem with the shock noise. So since the simulation is a zoom in, the shock noise does not follow the usual 1 over the number density law. So to solve these, we wrote a new power spectrum estimator based on the Fielmann-Kaiser-Peacock algorithm. And it's working, so now we can predict the linear structure formation in the early stages, and also we can see the nonlinear structure formation with this power spectrum estimator. But we have dark matter density fields, so we can also identify dark matter halos. At least we have to. So the available halo finders are not designed for this topology. We have zoom-in simulation, so the smallest halos only resolve in the central region, and larger halos are much bigger volume. We wrote a new halo finder, which is a spherical overdensity halo finder designed specifically for this topology, and we can identify halos in this simulation, what I showed you. So now we have a simulation, codes that they can analyze, and we can also test the isotropy. So the gravity in a periodic cylinder is not perfectly isotropic. We can expect small anisotropic effects, and these can be mitigated by increasing the virtually the bulk size along the z coordinate, and can use the distribution of halo spins to calculate or check the anisotropies, and this is what I've done. And you can see this is the distribution of the halo spin. So the angle between the halo spin and the z-axis, and it's a flat distribution. I even plotted the 1 sigma error bar. So these test lambda CDM simulations show that they are isotropic. Halo spins can point anywhere in the simulation. So now we have everything. Now we can run rotating simulations. So the ICs should be generated in a rotating model using anisotropic linear theory, but there are no available initial condition generator for this at the moment. So we have an approximation. So just to demonstrate the late time effects of rotation, we use lambda CDM initial conditions, rotate them as a rigid body around the z-axis. So that'd be just a small amount of rotation, and with choice we can directly compare the rotating and the lambda CDM reference simulation because we have the same initial amplitudes and phases. So we selected the angular speed to 10 to the minus 2 times 10 to the minus 3. So this was suggested in the recent Sigeti article. This is actually close to the maximum allowed rotation. And we found that we have 1.5% increased expansion rate perpendicular to the cylinder axis. Which is around the same order of magnitude what the anisotropic expansion paper claim. So this is a good sign. And actually this is a direct result from the n-body simulation. So now we have a free boundary condition on the xy plane, xy coordinates. So if the dynamics says that the simulation should expand, it can expand, and also it can contract. And this is the two simulations. So this is the lambda CDM reference simulation. This is the rotating simulation with a very low rotational speed. So this is the response present day at 1 rotation every 500 billion years or so. So this is a very low rotational speed, so it is really hard to see the difference between these two. But if I step forward and backward at the final state of the Lambda CDM and this rotating simulation, you can see that this is actually the effect of the rotation during the whole simulation. So we're talking about a very small effect. And by just looking these, I cannot tell which is which. So, but as you can see, we are seeing the same structure because initially we use the same amplitudes and phases. So we can compare the halo spins directly in these cases. And you can see there is a slight boost. So the blue curve is the Lambda CDM simulation. The orange curve is the rotating simulations with 2 times 10 to the minus 3 per gigayear angular speed. And there is a small boost at the Fourier radius. If I'm using the Fourier radius to calculate the halo spins, so there's a small boost in which for the halos that are rotating in the same. So the angular momentum vector pointing in the same direction as the simulation angular momentum points, and also decrease. You can see a decrease in this distribution for the opposite direction. But this effect is very small. If I comparing the 2 points in here, maybe 5 or 10% difference. And of course, this is disappearing as I'm decreasing this radius. So if I'm zooming into the halos and calculating the internal angular momentum, this difference basically just disappears. So this is a very subtle change, and it is very far from the Shamir claims. But now we are running higher resolution simulations on the MACTI supercomputer in Helsinki. Actually, are running right now. So with that, we can even resolve properly Milky Way mass halos. And maybe we can see better what's going on with these models. So just in summary, the structure formation in rotating models cannot be properly simulated in periodic boxes. We define a new topology in which the simulation can be found. We implemented a new cylindrical boundary condition to the existing StePS code. We run rotating and non-rotating simulations and compare those and demonstrating the effects of rotation. And of course, the StePS simulation code is publicly available for it. Thank you for your attention.
Something like order the field rotation. Questions? Yeah.
I have one comment and a question. So the Oslo group. Yeah. So in the Oslo group, we made like 15 years ago or so a paper where we looked at a rotating Bianchi model and its effects on the cosmic microwave backgrounds. And we found that it could, at least at large scale, explain these large scale anomalies and an amazingly good fit to the data. But of course, we were very worried about small scale operations, and we basically left it there because we didn't have neither the knowledge nor the computational power at that time. I think it's interesting to take it up. But have you considered looking at the CMB, the effect on the CMB?
So I'm mostly focusing on n-body simulation, but the missing slide I actually wanted to mention the CMB. So yes, the rotation should leave an imprint in the CMB. Maybe this is too far. Yeah. So we expect at low L values, but I'm not a CMB guy, so I'm doing the other part, the late time universe with these models. But it would be interesting to see some constraints from the CMB and use that to run these simulations.
Yeah.
But again, we are talking about a very small amount of rotation.
Just a technical question about the way you did the simulation. Wouldn't you, in principle, just assume like Bianchi type background, Bianchi type background, and then perturb around it, like relativistic simulations?
Do you mean the initial condition generation?
No.
You're running the simulation? Yes. I don't see why wouldn't be possible, but the existing code works well on a non-rotating frame. And if we've got some deviations from it, the particle dynamics will handle that. So we will have some extra expansion, for example, in the XY plane.
Yeah, but there are like relativistic effects.
Yes, yes, this is a whole completely Newtonian picture at this point. So again, we are talking about a very small amount of rotations. Closed time-like curves or any weird relativistic effects.
When is omega not measured? Today or at the initial condition?
So this is measured today. So I scaled it back to the initial redshift and use that during initial condition generation.
And you scale it with 1/t.
I scaled it with, I believe it was a squared. It was a squared.
Okay, so the
A to the minus 2, yeah.
yeah.
Okay, so one last question.
Just wondering about the Shamir compatibility. How fast rotation would you need to produce that result?
I have only this simulation at this point. The rest of the simulations are running. So this is actually this 0.002 per giga-year rotation is very slow, but actually this is very close to the maximal allowed rotation by GR. So if you go beyond that point, you will have closed time-like curves at the cosmic horizon. And that will break causality.
There probably are.
Yeah, but the diameter of the simulation is much smaller than that. So this is why we're not using GR for the simulation. So we are stopping at 500 nanoparsecs. But yeah, I can run a bigger simulations, but with higher rotational speeds, but that wouldn't make much sense because that would break GR.
Okay, thank you very much, Gábor, again.